In this video, we are going to go over section 2.5, which is the basic differentiation properties. In the previous section 2.4, you guys are introduced how to take the derivative of a function using the limit definition, which was, so recall from section 2.4, you took the derivative by taking the limit as h approaches to 0, f of x plus h minus f of x all over h. Now, although this will do the job, but it was a very long process. Now in 2.5, I'm going to teach you some shortcut using the properties, so you do not have to use the limit definition all the time. So here are 4 theorems that we will be using to take the derivative. And all these were coming from, technically, from section 2.4. If you took limit of all these function, constant, power, constant multiple, and sum and difference, using the limit, you'll get the same result. So let's go back and then start with the notation. If y is equal to f of x, so in algebra, we learned that you can rewrite y as a f of x notation. Then f prime of x, y prime, dy dx, those are all representation of the derivative of f at x. So if you see f prime of x, that means take the derivative. If you say find the y prime, that's also same thing as find the derivative. Find dy dx, that means also find the derivative of f. So these are the following theorems. If you have a function and it's just constant, such as y equals 2, then the derivative of any constant function is 0. If you have a power function such as x squared or x cubed or any n real number, then we take the derivative. The derivative function will be, you bring down this power n in front, and then your degree of the power gets subtracted by 1. All these are made from the observation from 2.4. Now, if you have a constant multiple, say 2 times a function, then we can ignore the constant and just take the derivative of a function. If you have a sum or difference, then you can take the derivative by term by term. Okay, so those are the 4 theorems that we will be using to take the derivative. So let's begin with number 1. I'm going to erase all this so we can see the theorems clearly. Find the indicated derivative, y prime for y is equal to x to the 5th power. So y prime is, it represents the derivative. So in other words, take the derivative of a function. So I'm looking at this one, and then this to me looks like theorem number 2, because you have x raised to some power. So I'll be using theorem number 2. Your y prime will be simply your n, which is 5 in this case, 5, x, 5 subtract 1. Or in other words, y prime is equal to 5x to the 4th power. And that's it. So this is a lot faster and a lot easier because you can get to the derivative within 1 or 2 steps rather than applying the limit. So these properties will be it will come handy when you start taking the derivative. Okay. Number 2, we have find dy dx. In other words, find the derivative for function y equal to 1 over x to the 4th. So we want to convert this function to either theorem 1, 2, 3, 4, because we only have 4 theorems. Now, number 2 doesn't look like any of this. It looks like a division. However, we know that y equal to 1 over 4 is the same thing as x to the negative 4. You can rewrite it using a negative power. then you can see that we can use theorem number 2. It's like a power function, x raised to some power. So I'll use theorem number 2 again. dy dx will look like your n comes down and then you subtract by 1. So dy over dx will be negative 4x raised to negative 5. You can write it this way, or this is also acceptable, negative 4 over x to the 5th power. Okay. MyMathLab will tell you whether to express the final answer as a positive exponent. If they ask for the positive exponent, you would put this last answer. If they didn't say anything, you can write it as the negative exponent. So that's what we are going to be working on. We are going to be using some algebra to rewrite the problem so the problem looks like one of those 4 cases, 4 theorems. And then once we have everything looking like 4 cases, we can use the theorem to take the derivative. So let's take a couple more practice problem. And I also wrote on the notes related homework problems on my lab, so you can look at my number 1 and see the work and kind of use this one to complete the exercise. Number 3, 2.5, 11 on my MyMathLab homework. So you'll have some problem that is similar to the homework problems on these notes. Number 3, you can also use the related homework problems on MyMathLab number 10 and number 11. So they look like a division problem. Again, I mentioned that there's no division. We saw that on number 2. I rewrote the division into some negative power so we can use either of the 4 theorems. Now here, I can rewrite number 3, so I have to rewrite number 3 to look like one of the following 4 cases. And one way to do that is, well, f of x, 8x minus 7 over x. You can rewrite x as x to the negative 1, but it gets messy. So another way is you can separate the fraction, 8x over x minus 7 over x. That's possible. And then simplify. So x part cancels out. We have 8. And then this one over here, I'm going to rewrite this as 7 to the x to the negative 1. So it looks like a power function. Now, I'm looking at this, and this looks like a difference. There's 2 things being subtracted. So I'll be using theorem number 4, the subtraction part, where I take the derivative term by term. So let's apply that. So using theorem number 4, I'm going to take the derivative term by term. So f of x is 8 minus 7x to the negative 1. So f prime of x, now this first term here is a constant. So that's theorem number 1, constant. Any constant derivative is 0. Negative 7x raised to the negative 1, well, that to me looks like theorem number 3. Why? Theorem number 3 has a multiplication and some function. So I'm going to ignore that constant term and only take the derivative of the variable term. So I'm going to keep that negative 7 as it is and only take the derivative of this term right over here, which is a power function. So negative 1 comes down, and then you subtract by 1. So negative 7 stays, and then we only take the derivative of x to the negative 1, which is negative 1 x to the negative 1 minus 1. So this part highlighted in yellow is the derivative term. Let's simplify further. So we have negative with the negative makes positive 7, x to the negative 2. Or you can rewrite that as 7 over x squared. So we use theorem number 4 on the first step. Then each one we use separate theorem. Theorem number 1 and theorem number 2 and 3. So in one problem, you can use all the theorem that's possible. Okay. Okay. So I'm going to continue with number 4, and this try to give you some different example problems. So number 4 is another fraction problem, and this looks very similar to number 6 on your homework problems. So find ddx of 8x squared over 5 minus 4 over 3x squared. So anytime you have this fraction or roots or some negative or positive power, the first goal is to do some algebra to make it look like one of those 4 theorems. So this part here can be rewritten as 8 over 5, so dx, x squared minus 4/3 x to the negative 2. I didn't take the derivative yet, so you see the term ddx to remind me I have to take the derivative. All I did was rewrite the problem. So 8 over 5x squared minus 4 over 3x raised to the negative 2. I rewrote it so there's a constant times a function, constant times a function. So that to me looked like theorem number 3, constant times a function. So I'm going to be taking the constants alone and only take the derivative of a function part, the variable part. And then I do it twice, term by term, the subtraction. So let's begin with the first term, and I'll use highlighter to separate these two. So if I take the derivative of the orange term first, I'm going to have, ddx now disappear. So I'm going to have 8 over 5, we are leaving the constant term alone. 2 comes down the power rule, x 2 minus 1. Okay, so that will be your derivative for the orange term. Similarly, subtraction carries over. We are gonna leave 4/3 alone because that's the constant. Bring down negative 2 by using the power rule, x negative 2 minus 1. So this is theorem number 3 that I'm using. And also theorem number 2. I apply this power rule. And this will be your purple term, derivative. Now we are done with the derivative. All we have to do is simplify. So I'm going to be simplifying this first term, orange term. So 8 times 2, 16 over 5. X, 2 minus 1 is 1. Negative times negative is a positive. So 8 over 3, x raise it to negative 3. Or rewriting 16x over 5 plus 8 over 3x cubed is perfectly fine answer as well. let me pause for a minute and see if you guys are okay with number 4. And I'll move on to number 5. So again, I'm going to be rewriting each term on number 5 to more like looking like a power function. So let's do some algebra first. 1 over x to the 4th, I can rewrite that as x to the negative 4. Now the root, square root is the same thing as 1/2. Negative 5x is fine, and then 8 is fine. So we have 4 terms to take the derivative. X to the negative 4th, 6x to the negative 1/2, 5x or negative 5x, and 8. Term by term, 4 times. So let's start with first one. That's simple. That's number 2, x to the some power. So we bring down power, subtract by 1 using power rule. We bring down the power negative 4, x negative 4 subtract 1, that will be negative 5. Same thing here, I'm gonna bring down the power, and 6 remains the same by theorem number 3 because that's just a constant. So I'm gonna have 6 times half. Now 1/2 subtract 1, which is 2 over 2, that's negative 1/2. So that will be my new power. This is really 1 there, so 5 times 1, so negative 5x. 1 minus 1 is a 0. Any constant term, 8, that's 0. So my last term is a 0. Oops, I should not write this one because I'm done taking the derivative. Okay, so that's your term after taking the derivative. Now let's do one more step and then simplify. So I have negative 4 over x to the 5th. I'm just expressing all my answer in positive. 2 can be simplified with 6. 2 goes 6 3 times. So 3 over square root of x. X to the negative 1 is the same thing as 1 over x to the negative 1/2, which is 1 over square root of x. So that's why you see the square root of x on the bottom. Anything to the 0 power is 1, so negative 5 times 1 is negative 5, plus 0 is just 0. So this will be my final answer. Okay. So let's look at number 6. And after number 6, we have some application problem. We have 3 application problem, and then these will help you complete some homework problems as well. So this one again, don't be afraid of the fraction. Okay, it's just number. And these I have to take the term by term 4 times. It kind of looks very similar to number 5 here. So term by term, and it's a power function. So I just have to bring down the power, subtract by 1 each time. So f prime, bring the first power down. So 7 over 5 x to the, now 7 over 5 subtract 5 over 5, because 5 over 5 is 1. I'm getting 2 over 5. So that will be my new power. 3 stays as it is, constant. We do not integrate by theorem number 3. So constant k remains the same. And then we bring down the 4 over 5 down. Same thing, 4 over 5 subtract 5 over 5. I get negative 1 over 5. Negative 3 remains the same. Bring down the negative 2 over 5. X negative 2 over 5. Subtract 5 over 5, I get negative 7 over 5. And then minus 0. Why? Because constant is a 0 when you take the derivative. So we just have to simplify. So first term is good. Everything is positive. This here, I can rewrite that as a 12 over 5. And then I like to put a positive exponent, so x to the 1/5. Negative with the negative makes positive, so 6 over 5, x to the 7 over 5. And that's it. Okay. So the first 6 problems is pretty straightforward. All you have to do is take the derivative, and then you just have to do some little bit of algebra tricks to rewrite the problem so that it's easier to take the derivative. Next 3 problem is an application problem, so we'll do some little bit of interpretation and then doing more than just taking the derivative. So let's start with number 7, and this looks very similar to number 9 of your My Math problem. So we have a given function, f of x as a 7x squared minus 9x plus 2. First part is easy. They just want you to take the derivative. Part B asks for find the slope of a graph of f at x equals 3. Part C, find the equation of a tangent line at x equals 3. Part D, find the value of x where the tangent is horizontal. So let's start with the easy one, f prime of x. And this is very easy to take the derivative because those are the whole number. Term by term, 3 terms. And then it's also the power rule. Bring down the power, subtract by 1. So 7 times 2, 14, subtract 1, 2 minus 1 will be 1. This one really has a 1, so 9 times 1, so negative 9. Subtract 1, 1 minus 1 is a 0. Anything raised to the 0 power, 1. So you have 14 minus 9. This last term disappears because it's a constant. So part A done. Very simple, very easy. Now part B asks for slope at x equal to 3. Now, we saw that earlier in chapter 5, derivative function represents slope of a graph. So this represents slope function of f. So part B really is saying find f prime at x equals 3. That's what it means. Written language, f prime at 3. So we are going to take f prime and substitute 3. Now don't plug it into f. You plug it into not the function, but slope of the function. So I need to plug it into this. So 14 times 3 minus 9, which is 33. So this is your slope value when x equals 3. Part C, what is part C? Find the equation of a tangent line at x equals 3. So that means I need to find a whole entire equation. And from algebra, we know a couple equations to write a line. One of them is y equals mx plus b. Another one is Points-law form, y minus y1 equals mx minus x1. Now I'm going to be using this formula here. This equation, you can use either one, but it's just easier because I know the slope value, which here by b, your slope is 33 when x equals 3. And I also can find a point by plug it in. So this is a little bit easier because I know a point and a slope. Here I have to use intercept and I don't know that. I can find it, but it will be more work. So slope is already given, or slope we found it in part B. Now, what is a function value at 3? Not a slope value, function value. That means I have to plug it into back to the original because I want to know a point at x equals 3, a function value, point. So let's first find the point. So f of 3, that means 7 times 3 squared minus 9 times 3 plus 2. So that will be 7 times 3 squared, which is 9. 3 times 9 is 27 plus 2. So my y value will be 7 times 9 minus 27 plus 2. I get 38. In other words, this means x value was 3, y value was 33. So I have a point and I have a slope value. Point, which will go into here, and then slope, which will go into here. Then I get an equation of the tangent line at 3. So let's plug it in and do some algebra to find out the slope, find out the equation. So y value of my slope is 38. Slope was 33. My x value was 3. I'm gonna rewrite it so it looks like a slope-intercept form, doing some algebra. So y minus 38, 33x minus 99, adding 38, I have y is equal to 33x minus 61. Done. This will be my equation of the tangent line at x equals 3. Okay. Part D, find the value of x where tangent is horizontal. So I have to find x value where tangent is horizontal. So horizontal means it's a slope is flat, which means I'm really looking at where slope of the equation is equal to 0. Okay. So from part B, we already know the slope function. All we have to do is find where it's flat and finding the x value. Where is it happening? So my equation from part A, we know the slope function, which is 14 minus 9, and I'm gonna set that equal to 0. That's what it means. Let me make a note. The tangent is horizontal when the first derivative has a value of 0. Oh, I'm missing 14x. So all we have to do is solve for x. Add 9, 14x equal 9, divided by 14. So I have x is equal to 9 over 14, or approximately 0.64. Okay. I will pause for a minute and see if you guys are okay with number 7. And I didn't, the problem did not ask for this, but I'm going to be using a calculator to confirm this point. I want to show you what's happening visually. So I'm going to be graphing this function, and you know by this equation x squared, it's a parabola. A being positive means upward parabola. So where the vertex is, that's flat. That's what the tangent is, horizontal. Horizontal means horizontal line, flat. So it's saying that this point is happening when x equals 0.64 or about, because we rounded. 9 over 14 was a rounded answer as a 0.64. So let's check. The equation was 7x squared minus 9x plus 2. Graph it. And we do see this flat line over here, right? Right there. And that's going to be around 6.64. And that sounds about right, 0.69. So you can say calc trace 0.64. I typed it up here, and then you can see that it's very flat here, 0.64. So that matches up with our answer. Okay. Let's do a couple more application problem. We have 2 more. Let's start with problem number 8. Actually, there's a little bit of a, there's only number 8. It says problem 8 and 9 use the following information, but there's only number 8. The last one, actually, I put a homework problem. So let me erase this part here. Okay. So we'll do number 8, and then the last problem is actually, I directly got it from the homework problem, number 12. All right, number 8. If an object moves along the y-axis marked in feet so that its position at time x in second is given by indicated function, find instantaneous velocity function, that is f prime, the velocity when x equals 0 and x equals 4, and the times when v's function is equal to 0. And f of x is given as 5x squared minus 3x plus 6. In other words, f function is my position function, and then my f prime function, which is a v function, you can see that from part A, is my velocity function, my instantaneous velocity. So starting with part A, let's begin finding v of x, which is just the derivative of my position function. So what is the derivative of this here? Then v of x is, again, this is an easy one, term by term using the power. 2 comes down with 5, multiplying, I get 10, subtract 1, 2 minus 1, 1. Negative 3x is just negative 3. 1 comes down, multiply with negative 3. 1 take away 1 will be 0. And 6, that's the constant, so it's 0. Done. Part A, we are done. Pretty simple. Part B is they just want you to take they want you to find the velocity value when x equals 0 and x equals 4. In other words, it's asking you to find the velocity value when x equals 0 and then when x equals 4. Okay? And we know the velocity function given by A. We found this, so all we have to do is plug it in. So we have 10 times 0 minus 3, so which is equal to negative 3. We have 10 times 4 minus 3, which is 37. If you want to, you can give a unit, so feet per second, feet seconds, 37 feet per second. Find times when velocity is 0. That means no moving. When is it stop? When does the object stop moving? So that's going backwards direction. Find x, because that's the time, x represents time, when the velocity value is 0. Well, the velocity function is 10x minus 3. So we can solve for x. So when 3 over 10, so 3 over 10 is 0.3 seconds. The object is not moving. All right, last problem to end the section. And this is, again, another derivative function, okay? Practicing derivative in application problem. The total sale for a company in millions of dollars t month from now are given by a function s of t, 0.02 t cubed plus 0.7 t squared plus 8t plus 2. Part A, it's asking you to simply take the derivative of this function. Part B, take a look, find two different values, s of 5 and then s prime of 5. So the first one, you're going to plug it into s function here, and then second one, you're going to plug it into part A function. And then the last part is asking you to interpret what that means. So let's begin with the first one. Find the derivative. Find the derivative. So we are going to be taking this function here. Okay. And then take term by term. Power function, so the first term, 0.02 stays, 3 comes down, and then subtract by 1, so it's 2. 3 take away 1, 2. Same thing, 0.7 stays, 2 comes down, t, subtract by 1, you get 1. 8t is just 8, and then 2 disappeared. Let's simplify further. So I have 0.02 times 3, which is 0.06 t squared, plus 0.7 times 2, which is 1.4 t plus 8. Done with the part A. Part B is also easy, just evaluating. This first one goes with the S function. The second one goes to the S prime function. So 5 means plug it in t value for 5. So first one 0.025 cube plus 0.75 square plus 8 times 5 plus 2. So using calculator, combining all those, I get 62 as the final answer. Second part to part B, now I'm plugging it into the S prime. So that will be into this function here. So 0.065 square plus 1.45 plus 8. Plug it in into the calculator. I got final answer as 16.5. Technically, $1,000,000. Okay, so what does these mean, right? So we did 5, but I mean it's the same thing. S of 10, that's just when t value is 10 and you have 172. So what does this mean? Well, S function represent what? Total sales, right? So we are looking for word total sale first. That one way to think of it is that, right? So by the process of elimination, I see that the only thing that has total sale, because S represent total sale, is A. Total sales of 10 months, that's good. T represent months, so 10 will be $172 million. A is the only one that works. Then what is S prime? Well, recall what is the derivative function mean? Derivative function represent rate of change. Okay, we saw that from previous part when we first introduced derivative. So I need to look for, well, it's not going to be total sale because that's S function. I'm looking for some kind of a rate changing. And the only thing that has a rate involved is this here, rate. In 10 months, that's your T, the sale will be increasing because we have a positive value at a rate of 28 million per month. So final answer will be D. That's it for section 2.5. And for the next video, we'll begin at 2.7.